Hello students, in this video we'll see an example of computing the inverse of a matrix by computing powers of the matrix and showing that it satisfies a certain polynomial relationship. Let's consider the matrix A, which is 0, 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, and then 1, 1, 1, 0. In other words, this is the matrix of all ones except the diagonal has a 0 in it, okay? Excellent. Now, let's find A inverse if it exists. Okay. And so here's the idea. What I'm going to do is I'm first going to compute A squared. You might not see why that's the case, but it looks like there's going to be a lot of symmetry. So if we compute A squared, for example, what will we have? 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, and then 1, 1, 1, 0, and then do it again. 0, 1, 1, 1. 1, 0, 1, 1, 1, 1, 0, 1, and then 1, 1, 1, 0. Let's check and see what we get over here. So in this first entry over here, what we're going to get is we're going to get a 0, a 1, and a 1. That's going to be a 3. Then we're going to get a, let's see, we'll get a 2. Then we'll get another 2. And then we'll get a 2. Okay, great. And then what? And then the next thing we're going to get is the following. So if we do the next row and column, we'll get a what? The 0, 0, and then we'll get a 2. Then we'll get a 3. Then we'll get a, let's see, we'll get a 2 again. Then we'll get a 1, a 0, a 1, and a 1. I'll get another 2. Great. Then let's do the third row. We're going to get a 0, a 1, a 0, and a 1. So we're going to get a 2. Then we're going to get a what? Then we're going to get a 1, a 0, and then a 0, and a 1. That's another 2. Then we're going to get the transpose of this thing. So we're going to get a 1, a 0, and a 1. That's a 3. Then we're going to get a 1, a 2, a 0, and a 0. So that's a 2. And finally, let's check this over here. We're going to get a 2 over here, as we can see. Then we'll get another 2. Then we'll get one more 2. Then we'll have a 3. Okay, so that may not seem like we accomplished much of anything by squaring the matrix because I've just created a new matrix that looks very different from A itself. However, the key feature in this is the following. The key feature is that there are 3's along the main diagonal over here, and there are 2's everywhere else. So if we take these 3's in the main diagonal and I want to try to factor this, what I can say is I can say this is going to be 3 times the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. The identity matrix, okay, that's just the four-dimensional identity matrix. And then plus what? So that's the 3's. And then plus, well, everything else is a what? There's going to be 2's below the main diagonal, then 2's above the main diagonal. That's just 2 times a copy of A. So that's going to be 2 times A. So we've now established a functional relationship for this matrix A. So what I can say now is I can say this. I can say that hence A squared is equal to what? Is equal to 3 times the identity plus of course, not times, plus 2A. Now I can rearrange this. I can write this as A squared minus 2A is 3 times the identity matrix multiplied by 1/3 to both sides of the equation. This implies that 1/3 of A squared minus 2A is equal to the identity matrix. And now we're in great shape over here because what we can do is we can now say that 1/3, so we can pull an A out of this, A times the matrix 1/3 of A minus 2 times the identity. Is the identity matrix. Now remember that in order to find the inverse of a matrix, we need to find the matrix B. So in other words, if I call this matrix over here B, we see that A times B is the identity, and therefore B is the inverse of A. So hence we've just shown that the inverse of A has to be 1/3 of the matrix A minus twice the identity 4. So let's write that out. What will this be? This is going to be a 1/3. Then A, of course, is 0, 1, 1, 1, 1, 0, 1, 1, then 1, 1, 0, 1, 1, 1, 1, 0, minus 2 0, 0, 0, 0, 2, 0, 0, 0, 0, 2, 0, and then 0, 0, 0, 2. And so let's count when we get over here. So we're going to have a what? Our final answer is going to give us a what? A inverse is the matrix. Well, we're going to have a negative 2/3. Then we'll have a 1/3, 1/3, 1/3, 1/3, 1/3, 1/3. The next row is going to be a what? Is going to be a 1/3, then a negative 2/3, then a 1/3, then a 1/3, then a 1/3, then a 1/3, then a negative 2/3, and then 1/3. And then finally a 1/3, 1/3, 1/3, and negative 2/3. So by using this polynomial trick, we were able to find the inverse of the matrix A very easily. In the case, even when A is a 4x4 dimensional, is a 4x4 matrix. Had we done row operations and elementary row operations, we had to do a tremendous number of elementary row operations. It would take up a ton of extra space. So this is a very useful technique to find a polynomial relationship that the matrix satisfies in order to compute its inverse. Thank you very much.